All right, welcome everyone. So earlier in the series of videos we've been watching relating to properties of determinants, we saw that in particular, if I take the product of some elementary matrix E and some matrix A, where both of these matrices are square and their products are defined so they're square matrices of the same size, that in the case where one of them is an elementary matrix, we have this property that we can calculate the determinant of the elementary matrix, the determinant of matrix A, and then take their products together. So the question is there a similar property for any two matrices? If I am taking the determinant of a product of any two matrices, can I just simply calculate their determinants separately and take their products? So before we justify that, let's consider the following claim here, and that is if I have two n by n matrices A and B, then if matrix A is not invertible, then the product of A times B, so A on the left, B on the right, that product is also not going to be invertible. So let's take a look at how this proof goes, and the way that we can prove this statement is using a proof by contradiction for anyone that's familiar with that proof technique. How proof by contradiction works is we are going to assume the negation of the statement we're trying to prove. So we're going to assume the opposite of the statement we're trying to prove, which is we're going to assume that A is not invertible and the product AB is invertible, right? So that would be the opposite of this statement that we initially said. So here I've got the opposite statement, and if I can prove that this statement is false, then its negation, the opposite of this statement, has to be true. So let's try and show why this statement that I have at the start of this proof is going to lead to a contradiction. Okay, so we are initially assuming matrix A is not invertible, but the product AB is invertible. And so by definition, if AB is invertible, then that means there must exist some matrix, I'll call it M, so that when we multiply AB on the right by this matrix M, we get the n by n identity matrix back. And now let's take a look. We have that the associative property for products, so I have that matrix A times the product of matrix B and M gives me the n by n identity matrix. So in other words, there exists some matrix, in this case B times M, so that when I multiply A on the right by this matrix, I get the identity matrix. So now this was one of the many conditions in the inverse matrix theorem. So by this observation, namely that there's some matrix that I can multiply A by on the right to get the identity, then by the inverse matrix theorem, A must be invertible. But that's a contradiction since we assumed A is not invertible. So we have just contradicted our initial assumption, so that assumption must not be correct. And therefore, the opposite of our original statement is correct, which is therefore that if A is not invertible, then it must follow that AB is also not invertible. And we could prove this very similarly, that if B is not invertible, then the product AB is not invertible. I will skip over that. It pretty much follows the same template of proof. So to summarize this entirely, what we can see is that if the product AB is invertible, then that tells me that both of the matrices A and B also are invertible.